Magandang araw mga ka-circle at maraming salamat po sa pag-join sa atin ngayong araw. Ako po pala si John Michael Reyes with a call sign of 4 Golf 1 Foxtrot Mike Juliet, a member of PUP Radio Engineering Circle, and I would like to welcome you all to the second part of our Propagate and Radiate webinar, Fundamentals of Amateur Radio in preparation for our NTC Class C Amateur Radio Examination. And our topic for today will be Element 3 for the fundamentals of electronics and electricity. I will start in a few minutes, but before that, please register now through the link or scan the QR code that can be seen on your screens. This will be one of the prerequisites for the e-certificate, and we can also be seen via our Facebook page, that's facebook.com/rec.org.ph, and to our YouTube channel, that's youtube.com/Radio Engineering Circle. And if you have any questions, you can type it on the comment sections of this delayed webcast, and our live volunteers will answer all of your questions. So again, just a reminder, the registration link is open until 7 p.m. only, so don't forget to register. And aside from that, you will need to answer and pass all the mock exam of 3 elements. For element 3, the mock exam link will be shown after this delayed webcast, so we highly encourage everyone to listen attentively to our speaker. Additionally, element 4 will be streamed on the following date and time. That's August 21 for element 4. Yun po, na uulitin po natin mga ka-circle, kailangan po ninyong sagutin ang aming mga online registration forms. Mabubuksan ninyo ito ang aming mga online registration form sa pamamagitan ng pag-login sa link o kaya naman ay pag-scan sa QR code na makikita nyo sa inyong mga screen. Ito po ay isa sa mga kinakailangan namin para po kayo ay makatanggap ng e-certificate. Hindi lang po 'yan, kailangan din po ninyong masagutan at pumasa sa lahat ng mock exam. Ang link po naman para sa mga mock exam ay pinapakita pagkatapos ng bawat webcast, kaya hinihikayat po namin ang lahat na makinig sa ating lecture. Also, we would like to invite you to join our circle, the Radio Engineering Circle Incorporated. Just log in to rec.org.ph/join to apply. We are a proud member of Philippine Amateur Radio Association and the Federation of Rapid Emergency Telecommunications Team of the Philippines. So I don't want to take much of your time, and here's the recorded lecture.
At the end of this course, we are going to learn, or we are going to review the fundamentals of electric circuit. That would be the first topic. We will go back to Ohm's law. We will differentiate the AC, the alternating current versus the direct current. We will also have to tackle the passive elements such as resistors, the capacitors and inductors, and selected semiconductor devices. We will also have an overview of test instruments that we usually used in the industry and of course in the school. So let's start. So let's first discuss how the word electricity was coined. It was started by Thales of Miletus during the 600 BC when he discovered that a stone, or when he was able to observe a stone, it's an amber that when he rubbed the amber into a fur. I think if I was not mistaken, it's a fur of a cat. He was able to observe that the fur of the cat was attracted to the amber, and from that term, and since from that term of amber, which means electron in Greek, they were able to coin the term static electricity. But prior to that, the discovery of magnetism was started from lodestone with a similar properties of an amber. It's also a stone used in mining. They were also able to observe that the lodestone was able to attract pieces of iron fillings. And the same is true with this amber. It just so happened that Thales of Miletus um, coined the term static electricity from this lodestone. So the picture, this is the lodestone. It is a translucent material, and the picture on the center, it's a lodestone covered with a fire, and this one is Thales of Miletus. Next. We have two types of electricity. The first one is static electricity, which means that it is electricity that produced by friction. So when you rub a certain material, for example, when you rub your comb into your hair and put pieces of paper, it will attracted to it. So that's static electricity. It is due to the friction, or it is due to the force that you exerted on that certain body Another one is Another one is dynamic electricity. For us to produce a dynamic electricity, it needs a source, for example, generators, batteries, etc. So that's the difference of static and dynamic electricity. Now let's examine this picture. This is a battery, and this is a lamp. This is a bulb, and there is a path between the battery. So you can notice here that the arrow pointed from negative to positive. So this picture suggests the electron flow of the circuit. So there's a path, there's a load, then there's a source, and of course this is a closed circuit. So later on we will differentiate what's the difference between the electron flow and the conventional flow. I'll try to put my pointers. Okay. This is it. So, next. But before that, let's go back first to the atomic structure. How does the electron flows from this circuit? Let's examine first the atomic structure. So this is an example of an atom. There are 2 pointers. Okay, anyway. So this is an atom. The blue at the center is the protons and the neutrons. They are located in the nucleus of an atom. And orbiting around the nucleus is the negatively charged electrons. So the red ones are electrons. The protons has a positively charged and the neutrons are neutral. So what do we call the electrons that are on the outermost shell of the atoms? We call that the valence electrons. So these are the valence electrons or the electrons outside the shells. The shell. They are the electrons that have the tendency to move or to declutter themselves from the atom to facilitate the flow of electrons. For example, if we are going to apply an energy here, for example, it's a thermal energy or electric potential energy, there is a tendency that this atom from this, that this electron from the outside of the shell will detach itself from the valence shell. And this facilitates, as I was saying, the flow of electrons. So when this, wait, I'll just put my pointers. Okay. So assuming that this assuming that this electron is being applied with an energy, for example, a 10 or typically 1 electron volt or higher, this electron will move out from the shell and it will become free electron. But before that, let's first discuss the three different materials. The first one is valence electrons. It determines the electrical properties of an element. The first one is a conductor. Conductor typically has a less than 4 valence electrons. Example of conductors are copper, which only has 1 valence electron, and typically one of the best conductors aside from silver. Another one is semiconductors. Semiconductors are either conductors or insulators depending on the energy that is being exerted on them. Example of conductors are silicon, germanium, and gallium. Next, insulator. Insulators has more than four valence electrons. Example, they have the resistance to impede the flow of electrons. Example of these are rubbers, our insulating materials like the one that coats the copper wires. Those are examples of insulators. Okay, so as I was saying, this is the valence. As I was saying, when you're initially this electron is in this part of the valence shell. Assuming that you applied an energy here, for example, heat, these electrons will declutter or detach itself from the valence shell, and this becomes the free electrons. These free electrons facilitates the flow of electrons, or these are the electrons that flows in your circuit. And what will happen to this to this part where the electron detach itself? This will become a hole. This will become a hole, which also capable of inviting another electron to attach itself from this hole. Since the electrons is a negative charge, we can treat this hole as a positive charge. Though the positive charge are in the center of the atom or in the nucleus, we can treat this as a positive since the absence of a negative could be a positive. So, and now from the flow of current, we have the first one is the flow of electrons, or the electron flow, which travels from negative to positive. And the other one is the conventional flow, which we usually discuss in the classroom setting. Conventional. It's the flow of it's the flow from positive to negative. Next, before that, let's first discuss the Coulomb's law. Coulomb's law states that opposite electric charges attract, and like electric charges repel. assuming that we have two protons having a positive charge on each other. So these positive charges, or these same charges, will repel each other. Next, if they have opposite charges, for example, a proton and electron, they will attract with each other. And same is true with the uh, with same electron. So let's focus on two electrons at first. Now, uh, one electron contains a charge of 1.602 times 10 raised to negative 19 coulombs. So that's the charge per electron. Next, this is a copper atom. So we will focus more on the copper atom. And this is your wire. In a wire, it is expected that a bit, since this wire is composed of atoms, let's zoom the part of this copper wire. This picture looks, this picture is the atom, is the copper atom. Okay, let's go back to the circuit. Let's go back to the basic circuit presented before. Okay, let's first focus on the electron flow, which means that the electron flows from negative to positive. Okay, let's examine the path. Okay, this is your path, and let's enlarge it. So in the path, assume that these are the copper atoms on the path of the, or these are the copper atoms on the wires. So we have a one valence electrons from the valence shell. So these are the electrons. So assuming that the electron was decluttered or detached from another atom, another copper atom, assuming there you applied an electric potential energy or you applied thermal, these electrons, since these electrons and another electrons here, since they are of the same charges, they will repel each other. So this free electron tends to push the another electrons from this valence shell. So the electrons here become a free electrons, and these electrons from another atom, the tendency is it will recombine with the hole here. Okay, like that. And again, this electron will push another electron here. They will a substitution, and this electron will again push the other electron, and it will follow until such time that that the electron from the last atom will also detach itself and become free electrons, and the cycle continues. Okay, the current is quantity of electrons passing a given point. It is defined as I is equal to charge over time, which a charge has a unit of coulomb, and T is second, meaning that your current, it is a measure of how fast the electron flows in your path in a given period of time. For a current of 1 ampere, it requires a 6.25 times 10 raised to 18 electrons that must flow in a conductor in a given second. So that's the equivalent of 1 ampere. So yeah, this is your conventional current flow. Your conventional current flow, it is your loop will be from positive to negative. It is as if that you are looking to the flow of holes. On the other hand, the electron flows, the path will have a loop from negative to positive. So that's the difference. Okay. Your voltage is a force created by a build-up of charge. So when you're, since the electrons, when they build up, it produces a force, and this will create your voltage. It also called as a potential difference between 2 points. That's the voltage, and it is noted as capital B, or sometimes it is E. And your unit is, of course, volts, in honor with Alessandro Volta. Resistance. Your resistance is the opposition to current flow. Um, uh, it is the opposition of the it is the opposition to current flow. So as we discussed earlier, one of the characteristic of resistance in their atom is that they have four or greater valence electrons. And for your electric power, this is the rate at which electric energy is transferred by an electric circuit. So it is noted by P is equal to VI, voltage times current, or it is equal to I squared R. Your I squared R is usually termed as the square law, and it is usually used in the circuit calculation as your conduction loss, your I squared R. Okay, let's go to the Ohm's law. Ohm's law states that the current flow through a conductor is directly proportional to the potential difference and inversely proportional to the resistance. So, assuming that this is your circuit, this is your battery, and it contains a volts. This is your resistance with an amount of resistance in it, and your current flow from your source to your load, well, there is a path. So what will happen if your voltage in your source decreases? Since your current and voltage is proportional to each other, it follows that your current will also decrease. How about if what will happen to your current when your resistance is being increased? So since they are inversely proportional, your current uh, will tend to decrease. So that's the relationship of the current, the voltage, and your resistors. So the three pyramid here just show you how to manipulate the V is equal to I times IR equations. Let's have an example. What is the voltage in a simple circuit if the current is 1 ampere and the resistance is 30 ohms? So again, your V is equal to IR. Your current is 1 amp and your voltage is 30. Your resistance is 30. It follows that 1 times 30 is 30 volts. That's example number 1. Another one. What is the current flowing through a load having a 12-volt measurement across if it dissipates 4 watts of power? Okay. So your given is 12 volts and a power of 4 watts being dissipated by a certain load. So your power, since your power is P is equal to current times voltage, and your current, manipulating the equation is equal to P over E, which is equivalent to 0.33 amps. That means in order for you to dissipate a 4-watt energy into a load, you need 0.33 amps from your 12-volt source. Okay, let's go to alternating current and direct current. Your alternating current comes from your generators, and your direct current comes from your battery. It may also comes from complicated or complex circuits that transform your AC to direct current, or what we call the power supply unit. For your alternating current, it is periodic, meaning that the waveform of your your alternating current repeats at a certain time. For example, this is your first period. After some time, after you completed the period, it will keep on flowing periodically. So from that, one of the characteristic of alternating current is having a frequency which is the inverse of your period. Assuming that this your period here is 4 seconds. So your frequency would equal be 1 over 4, and it will equal to 0.25 1 over S, or your denotation as hertz. For direct current, it doesn't flow alternately. It only flows in one direction. It's from positive to negative for your conventional flow, and negative to positive if you consider your electron flow. Next, alternating current has the characteristic of having cheaper to generate. Um, you can generate your alternating current using generator from your, for example, from windmill, from hydroelectric source, and etc. It is cheaper to produce alternating current compared to your direct current, which uses a chemical reaction from from certain chemicals in order for you to create a direct current. So it is expensive and limited lifespan. So the tendency of your of your battery, they will discharge in a in a short span of time. It's unlike your alternating current. As long as there is a generator, or as long as there is a source, it will not discharge. It will only depends on your generator, on your source of energy. Another one is ease of transmission. So how did we say that alternating current is easier to transmit? It is easier to transmit. For example, this is your power line. This is your wire, and this is your receiving end. So you can just, for example, your source is like this one. The amplitude is small. So when you are going to transmit this energy into the line, you can step up this using a transformer. You can typically you can increase it into 5 kilovolts in order for you to minimize the losses as you traverse the transmission line. And when you are at the receiving end, you can step it down into 220 VAC, which is being used by your household. It is unlike, on the other hand, in direct current, it is very difficult to transmit because they are prone to losses. For example, let's assume that what's in your transmission, what's in your um, uh, what's in the source of energy is a battery. Let's just imagine. For example, assuming that this is a 12 battery. If you are going to transmit this 20-volt battery from the receiving end, of course, what will happen? You cannot receive 20 volts at the receiving end. Perhaps it will decrease. It will decrease in a lower level because of the uh, because of the because of the losses or the drops that the transmission line will have. The question is, can we also step this DC voltage in a higher level, like what we will use, what we'll do in the AC? The answer is no. You cannot connect your DC into your transformer because it will shorted transformer. So that's the difference of alternating current and direct current. So another question here is, why do we still use direct current if alternating current is cheaper to is cheaper to create or cheaper to produce and has the ease of transmission? Um, this is because direct current is utilized by most of your electronic components. You cannot operate a diode. For example, you cannot operate a diode with an alternating current. Imagine if you are going to wait. At first, you can only forward bias this diode using a higher potential here. For example, of positive 5, you can only forward bias this by applying a higher potential in the cathode, in the anode compared to uh, the other terminal. So if assuming that this is a zero volt, you can only forward bias this using a DC current. What if your voltage apply in the terminal in the terminal of your diode is alternating current? The tendency is, so when your wave is at the peak, of course it will forward bias your diode. However, when you are in the negative peak, it will reverse bias. So it is better, or it is detrimental, or I mean it is imperative to use direct current to forward the uh, diode or other electronic equipment. So that's why we still use direct current from your alternating current transformed. Okay, let's have the simple circuit. A circuit is said to be closed circuit when there is a path. This is your load, this is your load, this is your source, and this is your switch. Since the switch is closed, the flow of current is possible. So this is called your closed circuit. On the other hand, we have the open circuit. It is said to open circuit when there is no flow of current, or uh, when the switch is off, or when the switch is open. So medyo nakakalito tong part na to. So closed circuit when your switch is on, and open circuit when your switch is off. Please don't forget that. Next, let's focus on a source. We can have a different source. First, this representation is a DC source coming from a power supply unit. This one is your AC source, alternating current. This is a battery, and this is your cell. And another source is a current source. So let's differentiate the voltage source and the current source. So for ideally, your voltage source has a resistance of 0. That's the ideal. However, in a practical application, there is a series resistance attached in your source, which also have a drop. This is the ideal application or the ideal scenario of your voltage source. However, for current source, let's for ideal current source, it is in parallel position. For ideal current source, your resistance is infinite. However, when you have a practical current source, it is already connected in parallel. So this is the foundation, I think, or this is was taken from the or derived from Thevenin and Norton's theorem. Okay, next. We can also have a series and we can also have a series and parallel batteries. When you're going to have a series battery, of course your your battery will add up. For example, 1.5, 1.5, 1.5, a total of 6 volts. That would be. However, you cannot having a series battery, you cannot increase the ampere hour rating of your battery. On the other hand, on parallel batteries, you just need to parallel the batteries, and just be sure that your batteries have equal value of voltage. So it's 1.5, 1.5. Looking into this terminal, your total voltage is still 1.5 volts. However, you just need to be careful that your ampere hour rating is the same, which with all the batteries. The advantage of this is that you can increase the current capacity of your circuit using the parallel battery. Okay, now let's proceed to your passive elements. Passive elements, they are the elements that doesn't require external power for their operation. And another thing is that they cannot amplify the electric signals. You have your resistor, your inductor, and your capacitor. Later on, we will going to have an in-depth discussion with these three passive elements. Let's first discuss your resistor. The formula for your resistor is equal to rho L over A, which your rho is your uh, is this is your constant, is your constant or proportionality constant depending on the material that you are going to use, meaning that your resistance is inversely proportional to the length of the material, and inversely proportional to the area, the cross-sectional area, so that when you are going to increase the length of your wire, your resistance also increase. But when you are going to decrease the cross-sectional area of the wire, your resistance will on the other hand, it will increase. So these are the types of your resistors. We have the linear resistors. Linear resistors, they don't vary with the applied current or with the applied voltage in them. They're just constant. They just vary linearly. They are not their resistance value doesn't dependent on the applied current on them. Your nonlinear resistors, and other one is thermistor, which depends on its resistance depends in the temperature. Your photoresistance or resistor, or the LDR, your resistance here depends on the light. Your varistor resistors, this varistor resistor is usually used as a protection, usually in electromagnetic compatibility against your against surges and the flickers. And for your surface mount SMDs, these are just very minute version of your resistors usually used in the electrics in PCB boards, which require a small footprints. Now let's go back to your fixed resistor, your carbon composition. You have your wire wound, which means that your resistor is being wounded by wire. Your thick film resistors and the thick film resistors. All in all, they have different applications. For example, it depends on the power that you need to dissipate on the resistors. You can, for high power, you can use thick film resistors, and for ordinary application, you can have just your carbon composition resistor. Next, for the variable resistors, the resistance values of these um, resistors varies on how are you going to alter it mechanically. They have their knob, your potentiometer, you have your knob, your rheostat, and your trimmer. Rheostat, it is using a tape that you can just adjust the tape for you to vary the resistance of your rheostat. So those are just a few examples of resistors. Okay, now let's go back on how are you going to read the resistor values. First is your SMD resistors code calculation. This one, it when this is a single digit, it is considered as it is being read as 0 ohm. And for this three digit 343, you're just going to take the first two digit, and your 3 here signifies your multiplication factor times 10 times 3. This is just true for a 3 digit. No. This is they usually code this use 3 just for kilo, like this one. 432. Again, you can observe that your last digit is also a 3, which is also a times 10 raised to 3. However, there are some resistors that uses alphabets like R, K, M, giga, etc. 38 are 1. So since the ones values, they don't just put it as 1 or 0, they just replace it with R. So your R signifies your decimal values. So 38R1 is 38.1 ohm. So there is an R here. For your kilos, for your kilo ohm resistors, they use uh, the letter K. So this is your the digit where the letter is being placed. That is your decimal point. So 3K2, which means 3.2 kilo ohm. This is also true with 2M1. Sorry, this must be M. This must be M. 2.1 M. However, for carbon composition resistor, we have a different way on reading the resistance value by using the band colors. So this is the example on how you're going to read. First, for a 6-band resistor, we have your first 3 digits signifies the digit of your resistance. Your fourth one is your multiplier. The fifth one is your tolerance. On this defines the variation or the deviation of the maximum deviation of the value of your resistance from its rated value, and your temperature coefficient. Um, your temperature coefficient suggests or define how your resistance vary with respect to temperature. The higher the value, um, the higher the deviation that might occur on your resistance when it's subjected to temperature or heat. So for your 4-band resistors, as an example, for your blue, for your brown, it's 1, your red is 2, and here we don't have the third digit. Since it is only a 4-band resistor, we treat the third digit as your multiplier, and the last band of color would be your tolerance. For a 5-band, the first three digit is considered, and there is no color here which signifies wait. Yeah. Your multiplier is red times 10 raised to 2, and your tolerance brown is 1%. Okay, let's proceed. You can have a series and parallel resistors depending on your application. So your series resistors, when you're going to series your resistors, the current that flows on the loop on each resistor is still the same. However, the voltage that is being read from each resistors is different. So we are going to use your voltage divider to find the voltage across this individual resistor. For your parallel, it's the other way around. The voltage on the terminal on the terminal of your on the two terminal of your resistors is the same with the other resistors, and it will be the same from your voltage source. The difference is that your current is being divided among the two resistors. So we are going to use uh, your current division. Just notice that the difference of your voltage and current division. In your voltage division, when you are going to find the voltage across R1, your numerator is R1. However, for the parallel, when you are going to get the current that flows on your, for example, uh, resistance 1, the current that flows here, you have to take the opposite resistor. Another application of paralleling your resistor is that, for example, you need a resistor of 10 ohm only. So your circuit only capable or is only allowed to have a dissipation for a 10 ohm resistor. Dissipation of power that must need to dissipate in a 10 ohm resistor. This is just the limit that your resistor must be 10 ohms. However, assuming that your current that will flow on this resistor is very high, that it exceeds the current rating of of your resistor, what are you going to do is that you have to parallel another resistor, uh, two resistors for you to cater the amount of power here. What will happen is that your current will divide by 2, assuming that you have a 20 ohm resistor and 20 ohm resistor here. Your current will divide into 2, and of course your power will divide into 2, which is other. um, you just have to split the resistor in order the power that you dissipate on this circuit is still the same on the power that is dissipated in the first resistor, which is only 10 ohm. The problem here is that it is sometimes costly, but there is also a trade-off, the cost and the certain problems that will be solved when you're going to parallel the resistor. Just, as I was saying, it is your it is in this example, it is your uh, current rating that is being exceeded by the applied current. So that's just an example of your application of paralleling resistor. Okay, this is the simulation I did. So we have a 15-volt source, and your resistance here is 500, and your resistance to resistor 2 is 1 kilo ohm. What would be the expectation in here? So I connected a differential probe to measure the resistance or the voltage that is being applied on each resistors. It is being noted that your current in your series circuit is still the same. It is only the voltage that is being divided. So your voltage, your probe 1 denotes the voltage across R1. So the voltage is here is 5. The green one here, it's not visible, I'm sorry. And your probe 2 having a 1 kilo ohm resistance, it is 10 volts. So the expectation is correct since when you're going to divide for example, when you're going to divide your VR1, your voltage source, 15 times your resistance, 500 all over 100 plus 5, 1,000 plus 500 is equal to uh, 5 volts. And your VR2 as follows will 10 volts. So that is that is just your, you can solve it by ratio and proportion. However, for your inductance, inductance. For your parallel circuit, again, your voltage across each resistor is the same. It is only your current that is being divided. So I measured the total current using this current probe from your source. The total current is 45 milliohms. It's there. And the current that flows into your R1, since it has a smaller, a lesser resistance, it is expected that that the current that a current that flows will that the current that flows in it will higher. So it is 15 milliohms, and your resistance and your current at R2, which has a higher resistance. I'm sorry. Napagpalit. Okay. So this one represents your current that flows in your R1, and this lower current is in your resistor 2. Okay. Let's proceed. Let's just have to process. Let's proceed with the capacitor. The construction of the capacitor is that you need to have a two parallel plates and a separator on the center. It is called dielectric. It can be an air. It can be other materials, but as long as it is a dielectric material. So when you are going to apply a voltage across these parallel plates, the tendency is that your positive here, your positive terminal here, it will push all your positive or your holes into this plate. And this negative terminal here, it will push all your electrons here. So what happens is that they cannot attract into each other since there is a separator in this part. So there is a build-up of your electron in the capacitor, which creates which is also treated as energy being stored on your capacitor. So the formula of your capacitance is equal to your permittivity times the area of the plate and the distance between the plate, and the unit for capacitance is farad. Okay. the standard and polarized capacitor. So let's take onto the circuit. So when you're going to apply a voltage across this capacitor, so there is a build-up of charge in this capacitor. So the capacitor is energized. So when you are going to move your switch, what will happen is that the stored energy in this capacitor, it will find a way to discharge it, and it is through your resistor and your diode. Since the capacitor, is it is a passive device that opposes the flow. It is a passive device that opposes the change of voltage. So what will happen here when the voltage that is being up, uh, when your source voltage is detached from your capacitor, um, it will try to hold the voltage as long as it can. So it will supply the stored energy. It will release the stored energy from your capacitor until such time that your it will decrease, and it will fully discharge. So this is your charging and discharging capacitor. That's how you discharge and discharge the capacitor. For the charging of capacitor, this is your voltage. Uh, there is an abrupt, there is a charging at the first portion. It is faster compared to the latter portion. And when you're going to discharge, at first it will be a very fast discharge, and it slows down until you reach your minimum value of voltage across your capacitor. So this is the flow of your capacitor, the charge and discharge of capacitor, assuming that that a switch is in your capacitor circuit. Uh, for example, in this circuit, when you continuously switch on and switch off your circuit, this will what happen to your uh, to the waveforms across your capacitor. Okay, the reactance of your capacitor is equal to 1 over 2 pi f times C. So when you apply an AC voltage in your circuit, it is being shorted. Since your frequency, assuming that for worst case scenario, it is your frequency is infinite. Let's just assume to visualize that your capacitor is really shorted in your it is really, the resistance of your capacitor is really shorted when you apply AC. So your reactance will become 0. And for your DC, when you apply DC here, wait. Yeah, when you're going to apply your DC here, sorry. It's yeah. It's your AC, it's 0. The AC can flow, in your resistor, in your capacitor. So AC can flow into your capacitor. However, DC cannot flow. So for DC, we have a 0 frequency. So 1 over 0, it is infinite. Your resistance for your reactance for your capacitor when this is applied is infinite. And with AC, it's 0. Again, your AC can flow in your capacitor. However, DC cannot flow. It is being blocked. You cannot flow. It cannot flow here. Okay. For your series capacitor, for your parallel capacitor, it is different from having a series resistor. For your, baliktad. Sorry, it's baliktad. For your parallel, you just need to add the individual values of the capacitance to have for you to have a total capacitance. And for your series resistance, it is the other way around. You have to get the inverse, the inverse of the sum of the inverse. It's somewhat complicated. Yeah. Types of capacitors. We have the ceramic capacitors. These are very small capacitors. Um, they have a low ESR. And your electrolytic capacitors, these are polarized capacitors. They are usually used as filters. And your supercapacitors, these are large capacitors that somewhat imitate the uh, I mean imitate the battery in such a way that they store a large energy. However, the difference is that they cannot perform well as the battery, but charging and discharging is faster compared to your battery. First one is the coupling or bypass capacitor. So when a noisy signal is being applied across a parallel capacitor, expectation is that it will filter out the ripple. So you will have a, uh, a clean output voltage from your capacitor across a parallel. And for your coupling blocks the AC. Uh, sorry. Your your capacitor, when it is being used as a coupling capacitor, it will block the DC component. So what will happen is that when the your AC voltage is being offset by a certain level of DC, the DC voltage is filtered out and your AC component will remain at the output of your capacitor. Another one is your power supply filtering. These are the application of your electrolytic capacitor that smoothens the pulsating DC from your rectifier. Okay, now let's go to inductor. Oh, this is your inductor. The composition of inductor is that your wire is being wound in a it is being wound in this manner. So let's first check this one. So when a current flows through a wire, a magnetic field is being induced here. This is your region. This is how your inductor works. So when you have your solenoids, yan umikot yung wire, the magnetic field will not cancel out. It will add up. So this is your inductance. So a inner core material, your length of the core, the cross-sectional area of your core, and the number of turns, which defines your inductance as your which is equal to your permeability, the permeability of this material times the square of your the square of the turns times the cross-sectional area over the length. So how does the inductor works? The inductor opposes the change of current. So in this example, when you are going to apply a voltage across a parallel bulb or load and an inductor. So at first, yes, your bulb will glow and your inductor will energize. However, when you switch off, so there will no longer be a source. The energy that the energized inductor will now begin to de-energize itself for him to for this inductor for the current for it to oppose the change in current. So it will try to oppose the change in current. However, it will discharge when in a certain time that you have already de-energized the stored energy in your inductor. So as expected, your bulb will not glow as much as before when there is a supply of voltage. Okay. For inductor, when you apply AC, it is open, and when you apply DC, it is shorted. Since your frequency, assuming when an AC, your frequency assuming it is infinite, so your reactance must be infinite. For DC, when you apply DC, of course your frequency 0, the reactance of this one is equal to 0, or it can be shorted. That's shorted. So series and paralleling of your inductor is the same as paralleling your resistors. Okay, types of inductor, you have your A core. Um, wala siyang core, but ang problem nito is saturation, madaling mag-saturate. Next is your iron core, and another one is your ferrite core. Ferrite core is usually used in high frequency application. Okay, let's go to semiconductors. We have your intrinsic. So this must be intrinsic semiconductors. You have your intrinsic semiconductors. First one is the N-type and the P-type, where your N-type, the dominant, the majority carrier here is your electron, and your P-type, the majority carrier here is your hole. So this is your silicon atom and germanium. Your silicon atom has a valence electron of 4. Same is true with your germanium. So for your semiconductors, they create a banding called covalent banding. So when heat energy is being applied, again, I'm going to explain, in your in the atom, the tendency is your valence electrons it will become a free electron. So this facilitates the flow of electrons in your semiconductor device or semiconductor material. So we have a doping. So for N-type, we have to, since in N-type, the majority carriers is electron, for you to have a, how should I call it, a faster or a more convenient of flow of electron, you have to increase your electrons by adding pentavalent impurities or atoms that has a 5 valence electrons. So these are your example, your arsenic, your phosphorus, your bismuth, or antimony. For P-type, you have since the majority carrier here is Hall, you need to add a impurities that also has a higher number of holes. So we are going to insert or dope trivalent impurities which only have 3 valence electrons, and of course you have a 5 valence 5 holes, rather 5 holes for your trivalent impurities. Yan. Okay, now let's proceed to diode. A diode is a two-terminal device which have your anode, your positive terminal, and your cathode, your negative terminal. So the construction of your diode is being made by attaching a P region and N region. This is a P-type semiconductor, and this is your N-type semiconductor. As expected, your P-type semiconductor has more holes, and and for the majority carriers of your N region is electron. So there is a PN junction here. For you to use the diode, you have to overcome your P junction, the voltage across this P junction, which is usually typically 0.7 for silicon. You have to overcome this PN junction for you to forward bias your diode and serves as a switch. So yeah, your depletion region is being created. So now let's review on how to go into forward bias and reverse bias your diode. Okay, we have 2 types of biasing, your forward bias and your reverse bias. In your forward bias, let's just note that in your forward bias, your P terminal or your anode must have a higher potential compared to your cathode. Has a lower potential here. It doesn't matter if you apply here a positive volts and a negative, or if you apply here a positive 5 or positive 3. Can the diode still be forward bias using this voltage across the 2 terminals? The answer is yes, since the potential in your anode is still higher from the potential from your cathode. So this is what happening when you're going to forward bias. Since a positive charge is being applied here, it will push all the electrons and attracts the it will push the holes and attracts your electron. Same is true with your negative terminal. Since this is negative, it will push all the electrons going to your positive terminal and same time attracts your holes going to your negative terminal. For reverse bias, it is different. When you're going to apply a negative voltage here or lower potential, um, your negative here attracts your hole since they do have different charge. And on the other hand, your positive terminal here will attract your electrons. Thus, you will have a greater depletion region and your current cannot flow through your diode. So technically on this part, your diode is off. And this one, since there is a flow of electron, it is on. Okay. Okay, this is the VI characteristic curve. Just show of the characteristic curve. So when you're going to forward bias, when you apply an voltage here, it will just flow here until such time that you overcome the voltage across the PN junction or the depletion region, and then your current will flow through it. For your reverse bias, on the other hand, when you apply a negative voltage across it, of course, it will not turn on. However, when the applied voltage exceeds your exceeds the rating voltage, the breakdown voltage, so masisira yung diode mo and it will have a reverse current. That's the difference. So there are diodes that is being used particularly for its reverse characteristic, and of course we have other types of diode that is being used for its forward characteristic. So we have your diode model. Your ideal diode model, it is just treated as a switch. Practical, there is a voltage, or there is a threshold voltage in series of the switch. And for your complete diode model, we have your RD, the resistance here. We have your still you have your threshold voltage, and when it is off, your resistance is being paralleled with the circuit. So that's the difference of your ideal, practical, and complete. So usually ang ginagamit dito is the practical diode model. However sa mga circuits that deals with high voltages, usually they consider ideal diode model for their circuit analysis. So ano lang naman kasi yung 0.7 volts, but eventually nakaka-contribute din siya. Next, your diode application. First one is your rectifier. Since your diode is a switch, so this is your AC, it is only being forward biased in its positive cycle. So your output, this is your pulsated DC. So this would be your reflection of your input. However, if you have a negative cycle, you cannot forward bias your diode, so it is off in here. So this is your this waveform is a waveform of your half wave rectifier. Another one is your clipper. It just clip your applied voltages. For example, when you're going to apply a positive cycle, it will forward bias your two diode here. Okay, so your output voltage is the sum of the 0.7 in here and your 0.7 in here, so it's 1.4. So anong nangyari dito what happened to this portion? This portion of the portion of your AC voltage that is being clipped ay napunta dito sa resistor mo. However, for your negative cycle, so it will start here. For your negative cycle, it will forward bias your diode here and it will reverse bias here. The two diodes prior to that diode. So what will happen to your voltage is that yung readout mo sa voltage is negative 0.7. So ito siya. So the other portion of your clippers is napunta sa resistor mo. So ito white na to. So that's the application of diode for clippers. So we can also have your an application of diode for clampers. Sinishift niya yung level of your AC, or nag-introduce siya ng DC voltage here, nag-offset siya. This is due to your capacitor. So yung na-charge na energy sa capacitor mo, so na-introduce into your waveform that it makes offset of your signal. So another one is your switch. Your diode can be implemented using can be implemented into an OR gate or AND gate. So your OR gate is that when your truth table is here. So when your input on A is low or zero, so your diode rather cannot be forward biased. So ang readout ng Y mo as your output is zero since walang current na nag-flow dito. Your readout mo is zero. So na-prove mo na your output is zero. However, for example, your input, your A is zero and your B is high or 1. For example, high voltage, typically 5 volts like that. So ang mangyayari here is that mafo-forward bias itong resistor, itong diode mo, and there is a current that will flow on your resistor. So your readout in your output is meron, it's also high. So that is your OR gate. For AND gate, so when your AND gate will only switch on, or your AND gate will have an output of high when both your input is also high. However, when one of your input is low, your output will also be low. So let's examine this one. So your output is 0 or low. Your input is 1. So what will happen here is that your output Y is 0. So since well, if you are going to, if you have a kunyari may separation sila dito, you can read a value of 1 here. Pero since they are connected, they are on the same terminal, since na short na to, na zero na to ground, na zero na to ground, since na zero na to sa ground, since zero na forward bias to, na direkta na siya sa ground, it follows na your output is 0 ground. Pero if you have your input 1 or high for both A and B, so ang nangyayari dito, since this is higher potential, your negative terminal is higher potential compared to this terminal, hindi mapo-forward bias to. So ang mababasa niya lang is hindi mapo-forward bias to, ang mababasa niya is parang nagkabit ka lang sa terminal na to ng DMM, so it will become 1. So that's the application of your rectifier, of your diode in rectifier, in your clipper and clamper, and of course, it is being used as a switch. Okay, you have your transistor. Dati, ang ginagamit prior to your transistor is your vacuum tubes. So, good thing is that na-discover nila Dr. Shockley, nila Burdin, saka Bratin yung transistor. So ito yung itsura ng first transistor nyo. The advantage of your transistor compared to the traditional vacuum tube is that is smaller and lightweight. Siyempre, mas magaan siya. Unlike your vacuum tube, it's very bulky. No heater requirement or heater loss. Your vacuum tube, kailangan mo pang painitin before mag-start. Unlike transistor, ready to use na siya. Rugged construction, efficient. Since your transistor only utilizes a small amount of energy or current or voltage, so mas efficient siya, unless dun sa vacuum tube mo na siyempre umiinit yun, and your init or your heat is being translated into power dissipation, so hindi siya efficient. And gaya ng sabi ko kanina, there is no warm up period for your transistor. So this is so medyo pa fast track ko na lang to. Your transistor construction, you have your NPN, your P layer is being sandwiched between the two N semiconductor. This is for your NPN. This is the symbol. And for your PNP, it's the other way around. Your N is being sandwiched across two P-type semiconductors. So the characteristic of this, for your emitter, it is being heavily doped. So ito siya, heavily doped. And your base is thin. So konti lang to and lightly doped. So yung ratio ng base mo, yung length ng base all over sa length ng transistor mo is 1:150. Ganun siya kaliit. Ganun kaliit yung ganun ka-thin yung base mo. And for your collector, it is the moderately doped part of your transistor. Pero itong collector na to, ito yung part na mostly dinadaanan ng current in your circuit, in your transistor. So ito siya. So you have to forward bias. Mag-focus na lang tayo sa NPN. You have to wait. Ano pala? Sige, ito. Sa P-type tayo. You have to forward bias your base emitter and your base to collector dapat negative, dapat reverse bias siya. So for it to be used as your amplifier. So yan, na forward bias, your base emitter must be forward bias and base collector must be reverse bias. At meron pa ibang application of your transistors in reference to the biasing, but ito muna yon. So ito yan. So your current, your IE will flow here, na-divide siya into your collector and your base. May napunta rin siya dito. Yan, na forward bias. Bakit nagkaroon ng flow dito is na reverse bias naman siya. Please note that your majority carrier here is in this portion is false or positive. So when you apply positive here, pinupush niya na to. So napupunta na siya sa base mo. And in your base, the positive here or the hole here is your negative carrier. Is your majority carrier. Sorry. Your hole here is your minority carrier, sorry. And your electrons here are the majority carrier. So ang nangyayari dito kapag nag-apply ka ng negative here, so since these are positive, di ba, majority carrier positive, nag-flow pa rin siya kasi na-attract to. Your positive is being attracted to your negative. Kaya nagkakaroon pa rin siya ng flow. And from that, your IE is equal to IC times IB. By the way, your collector current is also dependent on your IB with the proportionality constant of with a factor of beta rather. So yan. This is your characteristic curve. So nag-simulate lang ako. Since gaya sinasabi ko, your IC is dependent on your IB. So ito siya. For example, this is your naglagay ko ng current source. So when your IB, 0 ang IB mo, so hindi na forward bias to, you need to forward bias here. You need to overcome the 0.7 threshold voltage in this PN junction. So ayan siya. And so as you increase your IB, so yan, 0 micro, 10 micro, as you increases, it follows that your collector current also increases. So that's the relationship of your IB and IC. So ito yung different application, saturation. It is being said, the transistor is being said to be in saturation when your voltage in your base is higher compared to your collector. And your and it is also higher compared to your emitter. So nangyari dyan, na-forward bias to, na-forward bias din siya dyan. So saturation siya. For your cutoff, so for cutoff, reverse bias both your base emitter and your base collector. So walang flow of current, naka-off siya. Open yung circuit. For your forward active, ito yung application for your uh, ito yung state ng transistor for you to use your transistor as an amplifier. Meaning that the base and emitter must be forward bias and your base and collector must be reverse bias. We have also a reverse active pero hindi na natin masyadong i-discuss yan. So, hindi siya masyadong ginagamit or for switches, I think. Anyways, let's proceed. Ayan. Here is your transistor application. Kung makikita nyo, this is your first generation. Malalaki pa. I think this is from your picture tube sa TV. I'm not sure. So your second generation, yung maliliit, yung tatlo yung paa, yung apat. Until such time na they embedded it into a integrated circuit hanggang sa lumaki. And imagine your Core i7 Intel CPU. So your Core i7 CPU contains 2,600,000 transistors. Imagine kung paano nila pinagkasya yung transistors dito sa napakaliit na to. And that is initially tawag dito parang foreseen by your Moore's law. So another your transistor can be used as your amplifier for your amplifier circuit. When a small signal is being injected in your circuit, eventually it will amplified. Mas lalaki na yung amplitude mo. Ito yung usually na application of your microphone and speakers. Imagine nagsasalita ka lang sa microphones, ina-amplify ng speakers. That is the application of your transistor. Another one is your switch. Ito. So, if your control here or if your voltage here is na forward bias, so kapag na forward bias to, it follows that a flow of current, pwede na mag-flow yung current mo dito as long as this is being forward bias. However, kapag hindi naman na forward bias, yung base to emitter mo, your switch is off. Kaya tinatawag sa na switch. Yes, your CPU and your logic circuits or your integrated circuits are made up of transistors. Ayun, so that's all for your transistors. Now let's proceed to some of the test instruments. Test instrument, your ammeter. So ammeter is being connected with your circuit in series to measure the current. So ito yung connection niya. This is your source, this is your path, and this is your load. So kapag gusto mong kunin yung current, you have to make it series. Isi-series mo siya. Kailangang madaanan. Parang ang notation nito is your ammeter is para siyang resistor sana. Pero resistor with a few value of resistance. Ideally dapat 0. Ayan, para makapag-flow, para hindi siya mag-impede, para hindi siya mag-contribute sa impedance or sa resistance yung circuit. Yun yung ideal niya, kaya nakaseries siya. However, there are another instrument that you can instantly measure current. It's your voltage clamp. So ang gagawin ko na lang, kunyari, ito naman, ikakabit mo na lang yung clamp dito. And eventually, magkakaroon ka na ng reading. So yun yung advantage nito. However, kapag yung mga circuits na maliliit, for example, maliliit na circuit, you cannot use clamp meter rather. Hindi ka makagamit. So kailangan mo talagang mag-ammeter. So ayun siya. Just be mindful yung rating ng ammeter mo, hindi lang siya dapat ma-exceed. So ang principle ng ammeter mo is that merong nakakabit dito na may nakakabit dito na choke. So kapag nag-flow yung current here, kapag nag-flow yung current dito sa butas na to, since meron kang choke dito, meron kang magnetic field na ma-create and may mechanism siya dito na na-translate into current. So that's the mechanism of your clamp meter, a principle of your magnetic and electric principles. Next, your voltmeter. For your voltmeter, kung kanina sa ammeter, it must be connected in series. For your voltmeter, it's the other way around. You must connect it in your parallel of the portion that you're going to check the voltage. So ideally, your voltmeter must have a resistance of infinite. Dapat open siya. Why? Para hindi siya makaapekto dito sa flow ng circuit. Pero in practical application um, may mga resistance to pero very small. Ini-implement to using the arsinoval, parang mga ganun. Your galvanometer, mga ganun na part. Ganun yung sa, but that calls for another discussion. Your voltmeter must be connected in parallel. So just take note that ideally your voltmeter must have a resistance of infinite. Okay? For your ohmmeter, binabasa niya lang yung resistor mo. So dito sa part, kung nakatutok siya dito, if your probes are not connected, balik-baliktad kasi siya. Unlike dito, yung iba sa voltmeter mo 0, sa ammeter mo 0. Kapag itong resistor naman, ohmmeter, initially infinite siya. Yan, infinite. Yung dito part. So that when you're going to connect it in resistor or any material that you're going to test measure the resistance, so ayan, maggaganyan siya. Until such time na kapag na-short, 0 yung resistance mo. Yung difference, yung ohmmeter mo is naiiba kasi nandito yung 0 niya. Nalito rin ako dati dito. So you have your multimeter. Your multimeter is a single device na embedded na or andito na yung ohmmeter mo, ohmmeter, your ammeter and your voltmeter combined. So mas madali na lang siyang gamitin kasi iisa na lang gagamitin mo, and of course yung mas mura na rin siya compared sa bibili ka pa ng tatlo. You just have to be mindful sa knob nito na kung magme-measure ka ng voltage, edi ilagay mo sa voltage, or kapag AC sa AC, your resistance, o doon ka sa resistance mode. Just be mindful of that. Another instrument is your oscilloscope. So usually itong oscilloscope na to, ito yung ginagamit usually sa mga universities, pero itong ganitong level. So the purpose of your oscilloscope is for you to visualize the signals in your circuits. So kung gusto mo makita yung circuits mo, if it's sinusoidal, you can just connect your probes. Later on I will discuss the different probes. Kung gusto mo makita yung part na level, kunyari nagkaroon ng surge, gusto mo ma-measure. Kunyari yan, this is your voltage, kunyari nagkaroon ng surge. Itong surge na to hindi mo ma-measure using other test instrument. Your oscilloscope will be a way for you to measure yung mga complicated na waveforms na hindi natin nakikita. Ito naman, this is a specialized oscilloscope na parang computer na rin siya. Usually nga, parang computer na talaga to na pwede mo itong i-connect sa internet, pwede kang mag-Facebook dito kung gusto mo. And meron ding type na nakakapag-save ka na nalalagyan din to ng USB. You can connect your mouse and your keyboard here para kapag kunyari nag-save ka ng waveform, you can just easily vary, or you can just easily navigate your files in here. So parang computer siya technically na oscilloscope. And guys, ang presyo nito nasa millions. Medyo mahal talaga. So ito yung usually na ginagamit namin sa industry. Ito. Okay. Now these are your probes. We have your normal probe. Ginagamit usually yung probe kapag kunyari yung circuit mo is kunyari this is your circuit. So battery, may dalawa kang resistor, and this is your ground. This probe is used to measure voltage. Kapag nag-measure ka ng voltage in reference to ground, you have to use normal probe. Pwede mong gamitin. Kasi ang gagawin mo dyan, probe na to, i-connecta mo siya dito, assuming ito yon. And your negative, dapat i-connect mo siya sa negative or sa ground. However, kapag naman nag-measure, if you're going to measure a resistance, ito na part, ito, i-measure mo yung, voltage rather. Kapag i-measure mo yung voltage nito, hindi ka pwedeng, you cannot use a normal probe kasi hindi ito in reference sa ground. So, ang gagamitin mo dito is differential probe. Kakonect mo dito and dito. So, again, your differential probe, well, pwede mo rin itong gamitin kapag in reference to ground, pero specialize siya para sa mga voltage measurement na na hindi siya naka-reference sa ground. Okay? So you have also your current probes. So parang clamp meter lang din siya. This one here is a high current. Usually yan 1,500 yung rating niya. So meron din siyang dito, meron din siyang nahati na magnetic component dito, choke. And as usual, kapag may nag-ipit ka ng wire dito and may duman na current, i-induce ng magnetic field, and it being translated throughout this device, and ma-visualize mo na yung waveform niya using your oscilloscope. We also have your current probe here. Mas konti lang yung rating nito, usually nasa 30 amps for low current measurements. So your probes. So yun lang. That ends my presentation. Thank you so much for listening.
That's fundamentals of electronics. We sincerely appreciate you, engineer. Again, don't leave yet. Just wait for the link of the mock exam. Also, we would like to invite you to join our circle, Radio Engineering Circle. Just log in to rec.org.ph/join to apply. And we are proud member of Philippine Amateur Radio Association and the Federation of Rapid Emergency Telecommunications of the Philippines. Please like our page, like and follow our page, facebook.com/rec.org.ph, and subscribe to our YouTube channel. That's youtube.com/Radio Engineering Circle. Also, please join our daily evening net via Zello from 8 p.m. to 9 p.m. Join our channel. That's zello.com/rec. Again, thank you very much, everyone, for attending tonight's webcast. Make sure to attend the Element 4 webcast on August 21, respectively. Kindly fill out the mock exam form now through the link or scan the QR code that can be seen on your screen. This will be the prerequisite for our e-certificate. We're looking forward to seeing you again. This is your host, John Michael Reyes, for Golf 1 Foxtrot Mike Juliet. Have a great Sunday and good luck to your exam. Stay safe, everyone. 73.